Meet our quantum software instructors who just got dropped in a maze.
A6, you'll never get away with this!
This is a maze.
For our project, we created a quantum algorithm to efficiently solve mazes and get our teachers out. Hi, I'm Advithi.
I'm Nathan.
I'm Julia.
And I'm Revati.
And we are the Entangled
Axolotls. First, let's talk a bit about how our regular, everyday, classical computers solve mazes. As you can see here, the axolotl randomly picks a path and goes as far as possible through that path. If it hits a dead end, it backtracks to the last intersection to try a different direction, repeating until the end of the maze is found. This is called a depth-first search, and this approach is not ideal due to the sheer amount of time it would take to solve larger mazes. That's why we look towards quantum computers to make maze solving much faster.
Here I have a normal coin, and after that flip you'll notice that only the head side or the tail side will appear. And I can only really alternate between these two sides while the coin is in my hand, which is just like how a classical computer can only alternate between a 0 or 1 state in its bits. What makes quantum computers so special is that they have access to this sort of in-between spinning motion, where the exact value of the bit is not a 0 or a 1 until I catch it midair and measure it. Furthermore, quantum computers can perform logic on these quantum bits, or qubits for short, while they're in this superposition between 0 and 1, and that includes changing the probabilities of measuring a particular state versus another, since right now a coin flip is just a 50-50. This is somewhat like simulating both paths at the same time, which is why it plays such a major role in our algorithm. Our goal for our algorithm is something like what the axolotls are simulating here. We'll use a superposition of qubits to generate all possible paths to take through the maze, and find a way to amplify the chances of measuring the better paths, while discounting those that are invalid or simply too far away from the solution.
That's actually the main limitation of quantum algorithms, because although it sounds wonderful to check all possible states, what's really happening is that we have a superposition that gives a certain chance for each possible state. So we'll just need an algorithm to help stack the odds in our favor.
Now that you have the background knowledge that you need, let's get into the algorithm. We start off generating a maze by using an algorithm similar to the one that we mentioned before. More specifically, we are creating a perfect square maze, which means that there are no loops inside the maze.
First, we defined our fundamental directions by encoding them into a 2-qubit format. This means we represented north as a 0, 0 ket, south as a 0, 1 ket, and you can see the rest on the screen. We can then do some quantum math to split the path into more directions. We have some quantum bits that represent all the possible paths, including some invalid ones.
Now the goal is to determine the best path. We have to find the thinness of each path, or its distance to the maze exit. This comes in 2 steps. First, we have to determine where the path ends, or its stop point. We do this by creating new qubits. So now we have a big superposition where these new qubits can represent the current position of each path. So if we are to iterate through every single direction in every single one of the paths, we can essentially apply big mathematical operations to this huge superposition, changing the current position of every single path simultaneously. As a result, each path state will now correspond to its stop point. But wait, you may ask, how do you know if a path is valid? What if it goes through a wall? Well, I would like to introduce to you the is closed gate, which tells us if a desired move will break the rules of a maze. So there are 2 ways to implement this. The first one is using a large circuit, and the second is using a high-dimensional superposition. Without going into the specifics, one is more efficient for simulators, the other more efficient for quantum computers. Since we have limited access to the latter, our is closed gate looks like this. Basically, this is how we ensure that our paths don't break the maze's rules. Second, we have to determine how close each path's stop point is to the maze exit. A primary challenge here was memory usage. The amount of memory needed to simulate quantum bits on our classical computers increases exponentially. So around 30 qubits was really the limit for us. For reference, a 2x2 maze needs around 19 qubits, a 3x3 around 27, and a 5x5 around 47. So, to reduce the qubit count, instead of using Euclidean distance, we opted for Manhattan distance, which achieves similar results. Now, each of our many path states will correspond to both a stop point and a fitness.
The next step is to amplify the states that we want, and we'll do that through the use of an algorithm first proposed by a mathematician named Love Grover.
To understand Grover's algorithm more, imagine you are in a library with thousands of books and you are looking for one very specific book. And the only thing you know about the book is that it is the heaviest. One way to find it is you could put the books in a bag and shuffle it many times, like over here. This will cause the heaviest book to be at the bottom of the bag, which lets us find the book that we want. This is essentially how Grover's algorithm works. It boosts the correct solution so that it is more likely to show up when we measure it.
Now, after doing all of that, we can finally test our algorithm and see if our TAs can escape the maze. We are going to check the path by using a quantum simulator and turn the line of zeros and ones into actual directions.
As you can see, the program is now executing, and soon you'll see a list of every single state that the program measured and how many times each were measured. The path with the highest count, south-southeast-east, is, as expected, the correct answer.
Maze solving can be applied to a variety of purposes and future applications. Fundamentally, it's finding a route down a node tree, which can be an important part of many general cases of computer decision-making, including route optimization, delivery systems, and vehicle routing.
No axolotls were harmed in the making of this video. We are the Entangled Axolotls, and thank you for listening. We are now open to any questions you may have, and
Go
Go
quantum!
quantum!